Good afternoon. Welcome to this Makino Experience Center event where we'll be introducing the new Mag4 5-axis horizontal machining center for aerospace structural components. My name is David Ward. I am the product marketing manager for Makino, and for the next half hour or so we're going to kind of walk through the Mag4, give you a little bit of background on the history behind this machine and what we see for this particular industry. So when Makino brings new products to market and when we design new products, we're always thinking about what markets will those products serve. And those markets might be automotive, production machinery, certainly those are a couple of the real popular ones, die and mold, medical, even semiconductor. But what we'll be talking about today is aerospace. And when you get into aerospace, from a Makino standpoint, we have a very diverse product portfolio of machines to offer for aerospace applications. But in aerospace specifically, we really got to drill down another layer and think about where on that plane is this part going to be applied. And that may be in the structural side, things like wings, fuselages, those type of components, or it could be in the engine side. And those are very, very different areas of the airplane and very different materials. In the case of the structural components, we're typically working with aluminums. In the case of the engine components, we start to get into some of the hard metals, the titaniums, the nickel-based alloys like Inconel, that offer very different challenges. So the machines that we bring to market for aerospace are going to be thinking about those applications in a very different way. So unlike a lot of other machine tool builders, when we'll bring a product to market for the aerospace, if it's going to be on the structural side where we're cutting predominantly aluminum, what a lot of companies will do is they will take an existing machine and they'll put a high-speed spindle on it. There's our aerospace solution. If it's going into the engine side, maybe cutting titanium, their solution is to take an existing platform and put a high-torque spindle on it. We look at it very differently, and we look at it from a standpoint of a purpose-built solution where we'll design the machine literally from the ground up, thinking about what that material challenges are, what this machine is going to need to do to be able to ideally address those parts. So if we're thinking about titanium, we're going to be thinking very much about the structure of the machine, of the castings to be able to withstand those forces. In the case of aluminum, we actually started all the way back at the cutting tool, where we look at the really dominant cutting tool for aluminum structural parts is going to be a 1-inch end mill. And we looked at that 1-inch end mill to figure out how much material can we physically remove with this tool, and kind of worked backwards next to the spindle, next to the speeds of the machine, to the axis structure, and kind of worked backwards to figure out how to really optimize the performance of a 1-inch end mill. So that's kind of the stance that we take from a machine design standpoint. Now, the other thing we have to think about is the size of the parts, because everything that flies is not all the same size. We've got some of the components are very large. Bulkheads, fuselage components tend to be very large, but a lot of the other parts that fly may be very small. And so we have to have a family of machines that allows us to right size the solution for our customers. So we're thinking about that as well. So if we were to look at the lineup that Makino offers for aluminum structural aerospace components, it looks something like what you see on the screen right now. Where on the lower axis here, we've got the x-axis travel, quite a bit of range from, all the way from a small below 1,000 millimeters all the way up to something on the order of 20 meters of travel in X. And then Y on the vertical axis, and you can see some of the products sprinkled in there. So on the smaller side, if we shift all the way to the left-hand side, what we're going to see here are a couple of machines that are really designed for some of these smaller components like the latch that you see on the screen, or leading edge components. So along the edge of that wing, we've got a series of leading edges, starting with fairly large ones at the close to the fuselage, getting smaller, progressively smaller as it gets out to the end. So a couple of ideal solutions for those kind of applications. One in particular is a product we call the A61 NX5E. It has a 24,000 RPM spindle with a table-on-table rotary arrangement. Great solution for those kind of parts. And just a little spoiler alert, if you're going to be at IMTS 2024 this year, you will get to see the global premiere of the big brother for this machine. So a little bit of a teaser there. By all means, try to make it to IMTS and see that machine. Going to the other far end of the spectrum on that size range of parts, we see some parts like wing spars, wing panels, floor beams. These are parts that go axially out the entire length of that wing. So very long, skinny parts. And for products like those, parts like those, we have a different solution, a different series of machines that we call the A series. Starting with the A6, which is a 6-meter X travel, going all the way out to the A20, which has 20 meters of X travel. These are immense machines to address these very long, narrow parts. But really kind of the Goldilocks area of these parts and where you see the highest volume is in that center section. And this is where the Mag family of machines comes into play. Starting with the Mag3 machine and going all the way up to the new Mag4. So really what we're looking at parts-wise here are going to be wing rib type parts, which is what you saw in the previous picture. So these wing ribs are some of these center sections, and again, like the previous ones, they're smaller out at the wing tips and they get larger and larger as it gets close to the fuselage. And what we saw is that as we start to get towards the fuselage, these larger parts, not only do they get a little bit longer, but they're getting taller and thicker. And so with those, we started to see some parts being designed for these single aisle airplanes, like the one you see on the screen here, where they've got a thickness to them or a height to them that made it difficult for us to get all the way around these parts. So ideally, we'd like to be able to process these and get to all 5 sides of this part in a single setup. And we started to see challenges with the height of these parts where we were unable to get to the top and bottom because of the y-axis stroke on our previously largest machine. So that's really what's driven the development of the Mag4 machine. So the Mag4 is going to have 4 meters of X travel, 2.2 meters of Y travel. This is one of the big changes. 800 millimeters of Z travel. From the rotary axis standpoint, we have a tilting A-axis head that gives us plus or minus 120 degrees of tilt. And then we have a C-axis with an infinite 360 millimeter diameter rotation around that. Maximum workpiece, 4 meters by 2 meters by 700 millimeters, and the overall pallet is 3.5 meters by 2 meters. So if we were to peel away all the sheet metal and look at the axis structure, kind of a couple of things to note here. This is a split bed machine, meaning the table side is on one set of castings, the column is on a separate casting, and they are not physically connected. They are connected only to a foundation below them. And in the center will be a trough in the foundation that will house the lift-up chip conveyor or the chip conveyance for the machines, or for the machine. So from a kinematic standpoint, the table, which is going to house the pallet, is our x-axis. That gives us our 4 meters back and forth movement. And the column up and down gives us our 2.2 meters in Y movement. Both of these axes are really designed thinking about speed and agility. We're running at 33,000 RPM. When we start to do finishing, we're going to be moving very fast around these parts. So it's really ideal to make sure that these linear axes can move quickly. In the case of the x-axis, it is a rack and pinion with twin pinion drive for speed. In the case of the y-axis, it's a dual-driven servo motor ball screw axis, again for speed. Looking at the z-axis, the previous Mag machines, we would move this entire column in and out. With this machine, we're looking at a different design, and what we have done is we have gone to a ram-style z-axis. So that ram will move in and out to give us our 800 millimeters of Z travel. That ram style axis, one of the benefits of that is we've removed mass from the moving portion, and we're able to again go after these parts much quicker. So it gives us acceleration over 0.8 g in x and over a half a g in y and z. And here's what the full motion travel would look like. There's our x motion, y motion. We're kind of working our way around the entire perimeter of the x-axis and y-axis travel. Here's our z, in and out with the ram. And at the same time, we're moving the A and C rotary at the limits of their travels. So this kind of kinematics gives us ideal 5-sided accessibility to these large wing ribs and large workpieces. Now this is a new machine, but this machine is going to share a lot of the DNA or technology of its predecessors. All the Mag family machines carry this same Mag series design philosophy, and those are a single highly efficient spindle, a large range of motion with the rotary axis, horizontal orientation, and maximizing the spindle utilization. And I'll walk through each one of these briefly to just give you an idea of what that technology is all about. Starting with a spindle. Spindle's been an evolution over time. It started in 2005 with the original Mag machines being an 80 kilowatt spindle with 2 bearings. And then in 2012, we introduced a significant improvement in speed as far as performance goes. It brought it up to 120 kilowatts by increasing the number of bearings. And then in 2016, we brought that up to 130 kilowatts by increasing the spindle shaft diameter. So why would be doing this continuous improvement or this continuous adjustment of the spindle? And the reason really goes all down to the overall performance. The higher the power, the greater the stiffness of the spindle is going to end up giving us higher metal removal rates. Aluminum is a horsepower constrained material. So the more power that you have, the more stiffness and rigidity in the machine system, the higher the metal removal rate. So ideally what we'd like to see is a spindle that gives us full power, full horsepower, all the way out to its maximum RPM. And you can see here kind of in the history of the design, we started out at 80 kilowatt, would continue to build power all the way up to the maximum RPM. With a replacement which went to 120 kilowatt, again brought that power all the way up to the maximum RPM. And then with the 130 kilowatt, one nice feature of that is we now reach full horsepower at 26,000 RPM, which gives us the ability to even use some indexable inserted face mills, small face mills at this high power level, and then carry that full power all the way out through 33,000 RPM. And so what does that mean? Really, it's all about how many cubes can we get out of there? How many cubes per minute can we remove? So we started out at about 5.4 liters of peak metal removal rate. With the 120 kilowatt, we boosted that to 8.5. We are now in excess of 10 liters per minute for peak metal removal rate capability on this machine. And when you think about these parts, oftentimes when they start out with a billet of aluminum, which is the typical starting point for these wing ribs, for these spars, starting out at with that billet of material, 90% or more of the weight of that material is going to go out in chips. That is why it is so critical to have that peak power and that peak capability. So let's make some chips. Let's take a look at what it can do. So this is roughly a 2-inch face mill, 4-flute tool running at 33,000 RPM. We're feeding at 22,000 millimeters per minute, taking 10.5 millimeters axially and just shy of 2 inches of radial. So in this particular cut, again, we're thinking about peak performance. In this particular roughing cut, we're removing over 11 cubic inches, or 11 liters, 710 cubic inches per minute of material. Moving on, the large 5-axis range of motion, and specifically I want to talk about the compact rotary axis. It's pretty straightforward when you think about the linear axis. X, Y, and Z is very simple as far as the design goes. But when you start thinking about the rotary, how are you going to get those extra 2 axes to make that 5-axis machine? There's a lot of ways to do that. You can go with a trunnion, you can go with a knuckle style. In the case of these large parts, what the typical solution is to go with something that utilizes a tilt rotating spindle. And that's what we've done with a mag machine. That's what a lot of our competitors do, but there's a big difference. Many of our competitors, as far as the A-axis, are limited plus or minus 40 degrees or plus or minus 40 degrees, 45 degrees. They're doing that through a gimbaled style head. And the nice thing about the gimbal style head is it's very quick. However, when you want to get to 5 sides of this part, top, bottom, left, and right, if you can only tilt in 40 degrees or 45 degrees, you're not going to be able to get to that 5 sides of that part in a single setup without using angle heads, which really reduces the performance. So key difference in the case of the mag is our A-axis head is designed to go plus or minus 110. So we can get to the top and bottom, left and right of that part, and even reach a little bit behind if we need to have some draft angle on there as well. So that's a key differential. The other one has to do with the pivot point. And the pivot point is the distance from the rotation point of the A-axis out to the face of that spindle. Makino's design believed very strongly in keeping that pivot point as short as possible. And what that's going to do for us, if we look at it from another way, if you have a large pivot point and you're trying to get the top and bottom of the part, you start to run into the part, and as a result, you're only able to support a much smaller part. Whereas if the pivot point is nice and compact, both the center line of the Makino mag machine and the competitor here are the same. Because that pivot point is shorter, the height of the part that you're able to process and get to all 5 sides is much larger on the Makino solution because of that compact AC head orientation. Let's take a look at what does that mean. Here's an example of doing some shear ties. So now we've just rotated the A-axis around. We're attacking the bottom of that part, cutting those shear ties. That same sort of motion can be done on the right and left of the part as well as the top of the part. So one setup, 5-sided solution. All right, horizontal orientation. Why is that so important? If you think back about one of the comments I made earlier about starting out with billet type of work pieces, and 90% of the chips or 90% of the material is going to go out in chips. We really want to have gravity working for us, not against us. And so because of that, we are going to orient these parts up horizontally, even with a 1-inch end mill. If you look at the amount of chips that are getting generated there, it's immense. And many of these parts are really based on an outside frame of the part and then lots of weight reducing pockets inside the part. They want to create the pockets to reduce weight but leave the rib structure to create strength in the parts. Well, these pockets, if you're doing this on a vertical orientation, those chips are going to lay down in there in those pockets, and you're going to be recutting those chips as you're trying to create those pockets. So we're going to go with a horizontal orientation. We're going to make gravity work for us, not against us. And then we're going to put large amounts of coolant delivery all around the spindle to help wash those chips off of the part, away from the tool, and get those washed down into the chip removal area. So we've got a trough down in the bottom here with a powered conveyor in the bottom that is going to convey all the chips along the x-axis out to a lift-up chip conveyor system on the side of the machine. That lift-up chip conveyor system is going to include not only a drag type conveyance to get the chips out, to get the large bulk of the chips out. It's going to have a rotating drum filter, which is going to give us secondary filtration. And then finally, it's going to include a cyclonic filtration to polish that coolant and get it down to a very high cleanliness level. And then finally, we're going to have a suite of different technologies that are going to help us to maximize the spindle utilization on these machines. Some of them are very obvious. For example, an automatic tool changer, pretty common, But we're going to have very large capacity automatic tool changers on these machines so that you have the ability to have any tool that you're going to need for the variety of parts that you're cutting in that magazine and have it be able to stay resident and also have enough room for spares and backups. So the typical standard capacity is going to be 120 tools. We've got options to get up to 180. Spindle interface on this machine, I didn't mention this earlier, but at 33,000 RPM, we're going to rely on that HSK interface. It's an HSK-F interface, which means we've got 80 millimeters of phase contact from the tool to the spindle. Our overall chip-to-chip time is about 16 seconds. The other is a pallet changer. We're going to put pallet changers on here so that we can go from first chip or last chip of pallet 1 to first chip of pallet 2 in about 140 seconds. Now this video is sped up just for purpose of the webinar, but here's an example of how the pallet changer works. So the pallet is going to slide along the x-axis onto the pallet changer carousel. It's going to rotate 180 degrees. And it's going to have the second pallet on the back side of that carousel, and that pallet is going to slide in. So again, we've gone even on a very large workpiece with a 3.5 by 2.2 meter pallet. We've very quickly gone from the conclusion of the last part to the start of that next part. The other thing we're going to do is provide horizontal work setting capability. Now, if we had a part that billet starts out at 3 meter by 2 meter by 100 millimeters thick, that's about 3,500 pounds of workpiece. And to suspend that in air and get that up against that pallet and be able to bolt it up is very difficult. It's not ergonomic at all. So we're going to utilize something that we call a horizontal work setting station that is standard with the machine. So the pallet will come off of the pallet changer. It's going to slide onto the work setting station. Again, this is at 2x speed just for quickness of the video. And then it's going to lay down horizontally. So now again, we're going to have gravity working for us. We can use a crane to drop that billet part down on there and be able to walk all around that pallet, secure it to the fixture, and then prior to it pallet changing in, that horizontal work set station is going to stand that pallet up and slide it onto that pallet change carousel. Now the other really big game changer as far as spindle utilization goes is to pair up the Mag series machine with some Makino automation. And in the case of the Makino automation, the most common one that we see with these type of machines is going to be what we call the Makino Machining Complex, or MMC2. Across the population of machines that Makino makes, we have over 700 MMC2 cells installed in North America. These cells allow you to support pallets ranging from 400 millimeter all the way up to 8 meters. You can have anywhere between 1 to 15 machines, have offline work setting stations, pallet stocker stands to store the work or store the fixture while it's waiting to go into the machine. And all of those pieces of hardware are linked up by a rail-guided vehicle that is going to deliver the pallet just in time to that machine for machining. And the whole system is controlled. All system resources, your programs, your tooling information, your fixture information, your production orders, all of that is managed through the Makino MAS A5 cell controller. With these systems installed, we are routinely seeing spindle utilization north of 90% for the customer's machines. In the case of the Mag machines, here's kind of how that works and how the modularity of the system makes it fantastic for the customers. If you take an overhead look at a machine, the customer could start out with a standalone machine. Here's our base Mag4 machine. Here is the pallet changer. Here is our horizontal work setting station. The customer adds on the MMC automation. What we'll do is we'll add the rail-guided vehicle in with the pallet changer. We're going to redeploy their existing horizontal work set station and add in the stocker stands to give them complete automation with that one machine. Over time, as their business grows, they can add on additional pallets and additional rail to support more pallet stocker storage. Again, as they grow, they can add additional machines to that same cell. So, little solid model of what that might look like. We've got multiple machines. In this case, we've got 4 machines with the vehicle, which is the pallet changer that can pallet change and deliver to any of the 4 machines. And then you have your stocker stands here. This is where all your fixtures with work or the fixtures without work are going to be stored. These are your horizontal work set stations, so that for setup purposes, the pallets are going to be delivered to these for setup and then either taken directly to the machine or put back in storage waiting for the next available machine. So we have about 49 mag cells in North America. Those cells account for a total of about 140 machines in those cells. So about 50% of all of the mag installations here in North America are in cells like this. Just a quick video show you what one particular cell looks like. This is a Mag4 EX, which is the one size down from the Mag4. It's a Mag4 EX cell here. Those are the stocker stands. You can see the rotary pallet changer, which also serves as the vehicle. That's pulling a pallet out of the stocker stand. So that gives you a quick glimpse at what that automation would look like. So just to kind of wrap things up, we've talked a lot about the Mag series machine and specifically about the Mag4, which is going to be in the center area. We have been delivering Mag solutions to our customers since 2003. Smaller solutions for smaller parts like those leading edges, Mag1 and that A61 NX5E machine that we talked about very early in the presentation. And then for our very large parts, these longer wing skins, spars, beams, things like that, the A-series solutions. So that's kind of an idea of what that product lineup looks like for aluminum structural. Now, those machines have been extremely popular globally. Right now, we are pushing close to 500 machines installed globally. About 275 of those are in North America, so we account for about 60% of the global population. It's been an ideal solution for our customers doing these aerospace aluminum structural components. But as I mentioned early on, there's a lot of different parts that go into an airplane. If you're doing structural parts, those mag machines are going to be an ideal solution we'd like to talk to you about. If you're doing engine side parts, if you're cutting titanium, cutting Inconels, we have an entire different family of machines that are ideal solutions for that. We'd like to talk to you about that. So if any of this sounds interesting, reach out to your Makino representative. We can set up a visit. We can set up a virtual meeting like these Experience Center webinars, where we can have a very collaborative meeting with your team. You don't even need to leave your facility. We can send you a link to a meeting where we can collaborate through the Experience Center system here. We can provide you video to some of the mag machines that we have out on the floor. So it's a very easy way to learn more about the mag machines or about any of the Makino aerospace solutions without even leaving your facility. It's a great way to at least take that first step to learn more about the products. So if that sounds interesting, reach out to your Makino representative and have them set something up. So with that, we are going to wrap things up and we're going to go to the live Q&A. Be happy to answer any questions that you may have on your interface that you're watching this on. There is a chat function at the very top. If you click on that, you can use the chat system to type in any questions that you may have, and I'll be happy to answer those with time permitting. Thank you very much. Appreciate your time and have a great day. Bye. Okay, thank you for joining us today. Hopefully that was an informative Experience Center webinar for everybody to learn a little bit more about the Mag4 machine. Don't have a lot of questions that's come in, and I know we're running towards the end of the time for the webinar. One question I did see is when the machines go into automation, what controls what they run? And that really goes back to the my comment earlier about the cell controller. It's going to be the Makino MAS A4, a Makino Advanced System it stands for. That cell controller is really going to manage all of the components that go into making a part. It's not only going to manage the machines, it's going to keep track of the programs that are necessary for the parts. What are the conditions of all the tools? It even keeps track of, you know, the number of minutes on each, as well as the fixtures that are on the various pallets. So when a production order is entered in at the beginning of the day or beginning of the week, the machine is going to look at that production order, or the cell controller is going to look at that production order and determine which machines have the tools necessary. Are the fixtures available? Is the raw material available? And it will select the next available machine for that work to go to. And in the case of if there is a missing tool, for example, or a tool that gets damaged, it will find other work that is out in the cell waiting to be run, and it will adjust its priorities on the fly to ensure that those spindles keep running and that the spindle utilization is really carried to that highest level possible. So I'm not seeing any other questions coming in. So with that, I thank everybody for your time today, and hopefully we answered some of your questions on the new Mag4. And if you have any others, please reach out to your Makino representative. So with that, thank you very much. Have a great day. Bye.